That's just another way to say the energy. It's just like reporting a distance in miles or in feet. This is reporting the energy in joules or in electron volts. But which of these is probably more convenient? Well, notice that this is a teensy tiny number with 10 to the negative 19. It's much more convenient to use an ordinary number like 1.8, so we can see why electron volts are convenient here. But the number we originally got here was in joules because we used the form of H that was in joules. Okay. All right, so it's important to have this in your notes, how to do this kind of standard conversion between two different types of units. Okay, so now we've basically figured out everything about this red light. How do we interpret this 1.8 electron volts? This is not the total energy of the light. This is the energy of each photon in the light. So we should say what this equation tells you is the energy of the individual photons. I should have made that clearer. That you should put, I don't have room for this on the board, but you should put this in your flowchart. This is telling us the energy of the individual photons. This is telling us the energy of the individual photons with a wavelength of 700 nanometers. Okay. Now, the beam of light as a whole has a much bigger energy than this because it's composed of many photons. If you only had one photon, you'd have an energy of 1.8 electron volts. If you have two photons, you'd have an energy of 3.6 electron volts. If you have 1 million photons, then the entire beam of light could deliver an energy of 1.8 million electron volts. So all this number tells us is the energy of an individual photon. It tells you the energy of an individual photon. All right, and now we can already start to see where quantization of energy is coming in. If we think of light as a wave, it seems like the light wave should be able to transfer any amount of energy. It should be able to transfer any amount of energy. It should be able to transfer 1 electron volt, or 1.4 electron volts, or 1.46 electron volts, or 1.467 electron volts. If you just think of it as a wave, it seems like it should be able to transfer any amount of energy. But now we know that the energy is actually packed into separate discrete photon particles. The energy is packed into separate discrete photon particles. So actually, anytime an energy transfer happens here, this light can only transfer energy in units of 1.8 electron volts. Here we're getting quantization. This is the basis of that photoelectric effect. That was your last week's homework, so I don't know how much time we'll spend on that today. Maybe we'll get back to that for the final. But anyway, that was the basis of the photoelectric effect. So let's say that this red light falls on a surface. Well, could it deliver 1.8 electron volts? Yeah, it could. But could it deliver, say, 2 electron volts? There's no way that this light can deliver 2 electron volts. Even though it has way more energy than that, it can only deliver the energy in complete packets. It can only deliver energy in a complete packet on one single photon. That's the whole point of thinking of it as made out of particles. So the energy that can be transferred by this light is quantized. Does that make any sense? I don't know how well I explained that.
Yeah,
but
it does.
Yeah.
But then,
all right.
but then if the wavelength isn't changing of the wave.
Say again. What was the question?
Like if the wavelength of the wave changes,
Right.
then the packages, the amount of energy each electron volt would have would change.
That's right.
So then that would give you different values, but there's like
Right.
a constant. If there's a wave of a constant
Right.
wavelength.
That's right. So if you're sticking with a certain wavelength of light, there's only a set amount of energy that can be transferred. All right, and again, this should seem kind of weird because in ordinary life, you can kind of transfer any amount of energy that you want. So for example, let's say I want to transfer energy to this chalk holder. Well, I can move it a little bit and give it a little energy, or I can move it a lot and give it a lot of energy. And it seems like I can give it any amount of energy in between. I can give it any intermediate amount of energy that I want. But at the subatomic scale, things are quantized and only certain types of energy transfers are possible for certain photons. But you're right, if this was a different type of photon, there would be different energy transfers possible, but they would still be quantized, is the point. Okay, so that gives us that key idea of quantization. Now let's say then that we shifted to, say, violet light. We won't do all the math, although do you remember approximately what's the wavelength for violet light?
400.
Yeah, I guess that's about the bottom of the spectrum. I don't know if that's quite right, but about 400 nanometers. Anyway, the point is, this is a lower wavelength. That's right, per packet. Okay, good. So different wavelengths have different amounts of quantization.